There are 9 talks, I think. Perfect. Maybe you can try this if you want. Okay, looks like it works. Okay, so we have to start this last session of the day. So we have the pleasure actually to start with the Call 2025 Best Paper Awards. So we can start with a round of applause. So our first speaker will be Anai, so the floor is yours.
Thank you. I'll be talking about learning theory's application to identifying treatment effects. This is joint work with Yang Tsai, Alkis Kalavasis, Katerina Mamali, and Manolis Empetakis. So let me begin by defining what an observational study is. In an observational study, we see individuals. These individuals have different features that divide them into groups. So here the feature is age that divides them into two groups, young and old. And they also have treatments, which for us will be, ironically, smoking. And unfortunately, I'm sort of stuck with this terminology. And finally, they have certain outcomes. Okay? And our goal is to understand what the effect of the treatment is on the outcome, on the health of the individuals, or more specifically, what's smoking's effect on health. Okay. So let's talk about how to measure a treatment effect in the first place. There are various measures of treatment effects. A standard measure is called the average treatment effect, and it's the difference in the expected outcomes in two extreme worlds, one where everyone smokes and the other in which no one smokes. Okay? There are many other notions of treatment effects. Our techniques extend to them, but for the talk, I'll focus on this one. Okay. So before going to our results and prior work, let's talk about why a naive method of estimating the treatment effect doesn't work. So let's say we see these individuals. Then a simple estimator is to divide these individuals into two parts, one consisting of all the individuals who smoke, the other consisting of all the individuals who do not smoke, and then letting our estimate be the difference of the average health of individuals in the two groups, which in this example would tell us that smoking has no adverse effects on health. This approach, unfortunately, is wrong in general. And the reason it's wrong is because unlike a randomized control trial, the probability with which an individual takes up, or the assignment of this treatment to individuals is not randomized. It depends on various features of the individuals and other factors that we may or may not have observed. So in particular, even here, if we look at these, if we could, for each individual, observe two outcomes, one in which they smoked, one in which they didn't smoke, then we could compute the true ATE, and we would see that smoking does have a severe adverse impact on health. Okay. So this is one sort of crucial difference between estimating or identifying treatment effects and more classical learning theory problems like classification. Here, even if I give you infinitely many samples, I tell you the precise data distribution, you may not be able to identify the treatment effect unless you make some assumptions. Whereas in classification, if I specify the precise distribution of X and Y, you can always recover the optimal classifier. Okay. So because of this reason, a bunch of or many existing works give sufficient conditions that enable the identification of average treatment effect. And it's sort of known that these assumptions are not necessary. And this is questions dating back to very old work, at least to Rubin in 1977, who said that if you have certain more prior assumptions, you can go beyond these guarantees. And this is something we like to do in learning theory, characterize when we can solve a problem. And that's precisely what we do in this paper. We characterize the set of observational studies where the average treatment effect is identifiable. And this characterization is important because the standard assumptions people use are easily violated in practice. And in fact, this has led people to develop frameworks which relax these assumptions. And in these relaxed frameworks, they can approximately identify the treatment effect. So they can identify an interval in which the treatment effect lies. And in many of these relaxed frameworks, our techniques can be used to do exact identification of the average treatment effect. So now let's go over what these sufficient assumptions are. As I mentioned, the core problem is that the treatment assignment is not independent, is not randomized. So the first assumption people make is called unconfoundedness, and it roughly requires that conditioned on a person's feature that we have observed, the assignment of them to treat, whether they take smoking up or not, is IID with some probability. Now this probability can be different across two clusters, but within a cluster it's the same probability. The second assumption people require is overlap, and that just says that for each unique feature value, we need to have at least one individual who smokes and at least one individual who does not smoke. So here the cluster or the group of young people do not satisfy overlap because there's no one who smokes, whereas the group of old people satisfy. We have people who smoke as well as people who don't smoke. Okay. The problem with these assumptions are, as I mentioned, they are easy to violate. Let's first look at unconfoundedness. I mentioned that the treatment effect or the treatment assignment depends on the features of the individuals. If there is a feature that you have not observed that confounds the outcomes and the treatment assignment, then you can have confounding. And there are many other reasons, and also reasons why overlap can be violated. I won't go into them in this talk, but happy to chat offline about them. Okay. So let's move to introduce some notation before getting to our results. So the first step is to sort of lay out the problem in a learning theoretic framework. And here a somewhat important step is to have the right factorization of the joint distribution. And we factorize it into a marginal of feature and outcomes and something that we call a generalized propensity score, which is the probability that the treatment is assigned conditioned on an individual's covariates and outcomes. Notice that we don't really see both outcomes for each individual, so this may not in general be identifiable itself. Okay. So now this is some place where we introduce some new terminology over what is present in causal inference based on inspiration from learning theory. So we introduced two concept classes, one for the generalized propensity score and the other for this distribution of feature and outcomes. And we say an observational study is realizable with respect to this tuple if the corresponding generalized propensity score is in the class P and the other distribution is in class D. So in these terms, our problem is as follows. We want to characterize the tuples P and D that enable the identification of average treatment effect. And our main result is precisely such a characterization. It says that the average treatment effect is identifiable if and only if for every pair of densities in the class D, the ratio of their densities is not equal to the ratio of two generalized propensity scores in the other class. There are some mild conditions I'm hiding, and they're described more in the paper. Okay. And looking at a quantitative strengthening of the above condition, we can also estimate average treatment effect with finite samples. And here the error scales polynomially with the number of samples and some dimension that depends on these classes P and D. Okay. So let me go next into applications of our main characterization. So the standard setting is where overlap and confoundedness are both satisfied. Here we already know how to identify treatment effects. We considered three other cases. You don't need to know the terms on the right-hand side. I just keep them for information. But these correspond to cases where either overlap and confoundedness or both of them are violated. Okay. I'll focus on the second one in the remainder of the talk, but I'll quickly mention that the third one is also widely used in economics and has been deployed in important studies. Okay. So this is probably a slide I don't want you to take everything out of, but the high-level picture is that this captures some models out there which were called sensitivity analysis models. In these models, there is some parameter gamma that measures the distance of an observational study from unconfoundedness. For learning theory people here, you can think of this as some analog of adversarial models in causal inference, where gamma is the strength of the adversary. And here, existing techniques can identify the average treatment effect up to some gamma factor, or some factor which scales with gamma. Okay. In contrast, if you're willing to assume that your outcomes follow some standard outcome model, so say a generalized linear model is slightly more general, then you can exactly identify the average treatment effect. Okay. And we show similar results in the other scenarios, but for now I'll conclude. A key sort of contribution of our work is to connect learning theory with causal inference, like port some of the techniques over. And it's very interesting to see if learning theory can have other applications in causal inference. And that's the high level future direction. And some more specific questions are that our estimators are inefficient and are based on certain covering arguments. It would be very nice to have efficient and loss minimization based estimators. It would also be great to have some form of robustness to misspecification of these classes P and D. And finally, it would be nice to see if our identification results can lead to better estimates on real world data. So with that, I'll conclude. Here are the references. Thank you for your attention.
Thank you. Any questions?
Something about the dimension of P and D. What do you mean by that?
Yeah.
So the dimension of P and D, what do you mean by that?
So the question is, what do I mean by dimension of P and D? It refers to a few things factored in there. For P, it refers to the fat shattering dimension, if you're familiar with it, but it's the standard dimension that enables you to do regression. And for D, it's a certain covering number.
So the learning rate of AT is D over N or square root D over N.
So the question is, what's the precise learning rate for ATE? It depends on the specific scenario we are in. Typically, you get some dimension by square root of epsilon, or square root of n if you have n samples. But in some scenarios, we had a slightly poor dependence.
Okay, thanks. The speaker again. So can the next speaker come? So do you have the slide of the second presentation? Okay, so here we go.
Okay.
Okay, so our second speaker is
Arya.
Yeah.
Yes, you can just face my. That's the face for here. Hi everyone. This is a joint work with Hadley Black, Borna Saha, and Injan Zhu. The problem over here is that of graph reconstruction. So in graph reconstruction, this is sort of a pretty well-established area in theoretical computer science, where you are just given query access to a simple n-vertex graph. By the way, I don't know why this talk is in the Causality and Bandits session. But anyway, I will tell you about this no matter what. So, and you don't know the set of edges. So that's you know that the set of vertices without loss of generality is numbered 1 to n, and you are recovering the pairwise relations which make this graph. Okay, so by query access, we mean that we are sort of focusing, we are looking at a subset of these vertices and getting to know some information about the edge structure of that subset. What does that mean? One classical thing is this independent set queries. So where you just choose a subset of the vertices. You see there is a bunch of vertices, you choose a subset. Look at the induced graph and ask whether in that graph there is any edge. So that's the independent set queries. It's been around since 90s. There's Noga alone and a bunch of other folks started this. There's a series of work. And now the question is how many of that type of queries you have to make to reconstruct this graph in its entirety. Okay, So there are, so this is basically the way you are looking. Each query will let you see one part of the graph, and you are asking the sample complexity type questions. There are some applications, but it's okay. It's actually a basic combinatorial search question. So if you can answer this type of things, it's related to a bunch of other combinatorial search problems. So independent set queries, it's talking about whether a subset or a induced subgraph contains an edge. There is a bunch of generalization of this. One is, instead of asking whether there is an edge, you can give an answer of how many edges that there. This is called add queries, and it's also been studied in a bunch of papers which are listed over there. There is a maximal independent set query where you ask the question, you give a subgraph and ask to give a maximal independent set. So this is a more recent work from this year. There is a distance query where you basically give a pair of vertices and ask whether they, like, what is the length of the path in this graph for this, and you want to reconstruct the graph by making a certain number of distance queries. Okay. So in this work, we have one generalization of the independent set queries where we are looking at how many connected components are there in a given subgraph. So you give a subset of vertices, we're looking, an oracle will tell us in the induced subgraph how many connected components are there. Okay, so again, it turns out that this is not only a generalization of this independent set queries. There are some other combinatorial connections problems where this problem is related to. So this is the problem, and we are going to answer this thing. Okay, so what does connected component query means? So again, you basically see this is a graph. There is 1, 2, 3, 4, 5 vertices, and then suppose you're asked whether this green set of green vertices, there are 3 of them, how many connected components are there, and the answer is 1. The set of blue vertices, the vertices circled by that blue color, the number of connected components are 2. And then for the set of red, there is 1. So basically by asking these 3 queries, you can uniquely reconstruct this graph up to an isomorphism, right? So that's the. So you have made 3 queries. We want to characterize it for general graphs. Okay. Okay, I'm not going to go, because we have only 10 minutes, I'm not going to go into the motivations in detail, but there is actually a bunch of other problems that this one is related to. So there are some basic bounds. So you can have a trivial order of n square algorithm, because you can, instead of a subgraph, you can query an edge. And if there is an edge, the number of components is 1. If there is no edge, the number of components is 2. So by making n square queries, you will always be able to reconstruct the graph. Okay. So you can actually show that this n square is also a lower bound if the graph is arbitrary. Okay, so there's a trivial problem. You can just take this graph where it's a complete graph, everything is connected to everything else, except for one edge, right? And it turns out that if you do not query all n square edges, you will not be able to distinguish whether there is this graph and the complete graph. Okay, so that's the high level, but you can also show that there is, just by using something like Yao's min-max principle, that even with randomized algorithm, you cannot do that. Okay, so the lower bound is valid. So that means that this has to be parameterized by the number of edges in the graph in some way, right? Otherwise, the problem is sort of trivial. So we need to somehow have a bound that is parameterized by the number of edges in the graph. So to make this interesting. Now, if you do that, then there is an information theoretic lower bound, which is m log n divided by log m. So why is this, how this bound comes into being? Because if there is an m edge graph, the total number of m edge graph is sort of n squared choose m, because n squared is the total number of possible edges. So it's in that order. So log of that is the number of, is sort of the entropy of that space of the graph. And by asking each of the queries, your queries are number of connected components. What is the largest number there can be? Well, there can, of course, be n, not more than n. So you get something like m log n over log n, which is m. But you can actually, in the denominator, you can get log m because you can argue that the number of connected components in any induced subgraph is between the size of the subgraph minus m and the size of the subgraph itself. So since there are m options over here, so that you get that lower bound, or m log n divided by log n. So what we will show that actually this bound is achievable. So this is a lower bound. Now I'm going to give an algorithm that will achieve this. Probably I will not give that algorithm. I don't know how long. Okay, so there is an adaptive algorithm that gets to this value, m log n over log m. For non-adaptive algorithm, there is actually an order of n square lower bound, even when m equals to order of n. It's just, and we are also going to give a 2-round algorithm that gives m log n. So these are the list of result in this paper particularly. It's m log n plus n log square n. So one interesting thing would be to understand this 2-round algorithm, how this works. So in 2 rounds algorithm, we can, in the first round, we can approximate the degrees of all the vertices in the graph by making about n log square n queries. How do you do that? You just randomly subsample a bunch of vertices and ask the number of connected components in there. So by doing this, just by using some simple concentration inequality, you can show that every degree of every vertices can be estimated. Once you know the degree of every vertex, you can use this connected component queries to simulate something called an OR query, or a group testing primitive. Okay, so in a group testing primitive, you basically you want to recover a subset of some universe, and you are asking, you can query with another subset, any arbitrary subset, and it will tell you whether there is an intersection or not. You can show that the this type of queries can be simulated by making a small number of connected component queries. Actually, 2 connected component queries will simulate this type of things. So that's a pretty nice connection that that we could exploit to get this 2-round algorithm. So now let's give some intuition about why the non-adaptive lower bound works, because you can have this type of cases. So you see there are this complete bipartite graph, and on the other hand, you have a graph which is complete bipartite plus 1 edge, like this. So to distinguish these 2 graphs, you have to query some subset containing both u and v. And if you query any such subset larger than 2, then the number of connected returns will always be 1. Therefore, you will not be able to distinguish if you don't do n choose 2 queries. And this sort of is valid for randomized algorithm, again using something like min-max principle. So you have this lower bound. Now, how can you, how adaptivity can help is that you can learn structural information about the graph to inform later queries. So for example, I told you the group testing primitive. So this is actually how that happens. So if you have a vertex u, then you can query with the subset S and the subset S union U, and the number of connected components would be the same only if the neighborhood of U and S has no intersection. So this is how you make the connection with group testing. So that's how this is one of the observations that leads to the algorithm. So I'm just going to, so this is some detail about the technique that we will not have time to go over. So that's what we use to get this adaptive algorithm. Okay, so there is this is actually, this has some consequence. As I mentioned, it's connected to other problems, and there are some open problems. For example, for the round complexity of things, how things change from non-adaptive to adaptive is not very well accounted for. So that seems like the current, and then there are some techniques that we have used for this problem can be translated into other combinatorial search problems, can be of interest. Okay, so that's it. Thank you.
Thank you. Anyone quick question? Yeah.
So you have parameterized using the number of edges. I'm wondering if there are any parameters you can consider, like maximum degree of the graph.
I think if you do anything with degree, you will not get anything non-trivial from the number of edges. Can be something else, like free width, or it has to be significantly different from the average degree, which is the same as the number of edges.
Okay, thanks the speaker again. Okay, so our next speaker is Seok Jin.
Yeah, right.
You can go.
Hello, everyone. I'm here to present our work, Experimental Design for Semi-Parametric Bandits, and this is joint work with Jisoo Kim and Minano. So I'd like to introduce our setup. So we consider KM bandit problem with fixed feature set X, but we assume the real-world model follows some semi-parametric real-world model. So here is the model, and zero star is unknown parameter, and era T is sub-Gaussian noise. And a key difference between linear bandit is there is some shift term alpha T. So alpha T is arbitrary boundary shift, and it must determine prior to action selection, but it can be adversarial. And we only assume some mild boundiness assumptions for parameters and noise level and shift and feature norm. So this semi-parametric bandit problem has been studied in several works, and they are focused on contextual bandit setup, and they achieve D-root regret bound. And so our first research question is, can you achieve root dt, square root dt regret bound? And our second research question is, can you find some exploratory policy for this semi-parametric bandit problem, and can you get some best time identification or peg properties? It is related to some exploration thing. And in this talk, I wanna hide. I'm not going to hide locate terms in Taylor notation to emphasize the action cardinality dependency. I like to provide some motivating examples. So, first example is in clinical trials where the treatment are fixed, then subject can vary, and also baselines can change over time. So in this case, alpha T can be natural progression of the subject or baseline. Also for second example, in ad selection in a landing page and without access to personal information, in that case, alpha T can account the baseline clicking tendency of user. Also, it may account some external interference or broader trends. Now I'm going to explain our estimator. So assume some simple scenario. So we are sampling our actions from the fixed policy P, and we define feature mean as the following. This is the mean of features selected by the policy, and we define centered features. So centered feature is selected feature minus the feature mean, and it is mean 0. And we set orthogonalized gram matrix as some summation of outer product of centered features. And then we adopt some existing estimator from prior work. And essentially, we are doing rich regression with respect to independent variables as centered features and responses as reverse. So it's important that we are doing regression with centered features. Then that is difference between linear bandit case. Yes, and to describe the estimator's consistency, it can be followed from the following error decomposition. So when we decompose our error, so it is shown in here, and the second term is standard bias term in ridge regression, so it can be controlled easily. And for the first term, so there is some summation term, and we can see this term is martingale since tilde x is centered features and this is mean zero. So we can guarantee some consistency of the estimator. And honestly, this estimator technique is adopted from some causal inference like orthogonalized learning or partially linear models. And so when we see the matrix inverse norm term, it concentrates to t times of sigma p, where sigma p is covariance of the policy p. So to estimate the reward at feature z, it is very important to bound this matrix weighted inverse norm, inverse matrix weighted norm. But again, the difference between linear bandit case is the sigma p is orthogonalized. It means it is covariance, not second moment. For linear bandit case, it is just second moment. And also, I want to argue some parallel shifting things. So to identify for tasks like base time identification or Lagrange minimization, it is sufficient to estimate xi transpose zeta star plus c for some constant. So by setting c as minus mu transpose zeta star, then it is enough to estimate the reward for features xi minus mu. So bounding this matrix inverse norm is very crucial. Also, choosing a good mu is one of our challenges. And recall that sigma p is covariance, not second moment. And first, I'm going to present our optimization problem. So it is related to G-optimal design of orthogonalized regression. So we aim to minimize this error among our whole arms, but again, we need to choose mu, and the matrix inverse term is covariance of the policy, not second moment. So this is different from the linear bandit case, and since sigma p involved with third order term of pi, so it is more challenging than linear bandit's G-optimal design optimization problem. Now I'd like to present our algorithm to find some exploratory policy. We named it DEO. So first calculate BI. So BI is xi minus x1. And find G-optimal design for features B2 to BK. So this G-optimal design is standard linear bandit G-optimal design. And we write it as tilde P. And finally, we set our policy as P1 as half and Pi as tilde Pi over 2. And we denote this, our final policy as PDO. And also set our corresponding covariance of our policy as sigma DO. Next, I'd like to discuss the quality of our design. So recall that for linear bandits, when you solve some G-optimal design, then the optimal value is square root D. But for our design, the matrix inverse norm among the whole arms is bounded 2 times of square root D. So I'm not sure it is optimal, but still it is very favorable performance since our problem is much harder than linear bandit case. So we choose mu as x1. So we are shifting to x1, but it is sufficient to estimate. And also, this is favorable since our problem is more challenging than linear bandits. And the next main theorem is error analysis of our estimator. So this theorem is about error analysis. So prior work's error bound is d over square root t. So our work is square root d over square root t. So our result is slightly better with respect to dimension d. And prior work only depends on some Cauchy-Schwarz based analysis. And when we, as you know, like when you analyze estimation error via Cauchy-Schwarz thing, then we cannot achieve optimal rate with respect to dimension d. So again, it is sufficient to estimate xi minus x1. And also, this is optimal rate with respect to dimension d. And this is non-asymptotic. And okay, and given a G-optimal design, it is very famous that we can. There is a very famous arm elimination scheme, so we adopt it, but we use our previous result two theorems, using also orthogonalized regression and our error bound. So yes, we are combining this scheme. And first step is for survived arm at pace error, we find our design, and then we sample each action according to our design for this rate, and then we eliminate arms whose estimate rewards are larger than some confidence bandwidth epsilon L. So our elimination algorithm has regret bound of square root dt. And also, when we assume there is some suboptimality gap, then we can achieve logarithmic regret with respect to time t. So this is the first square root d late regret bound for semi-parametric bandit problem. And also, when the number of actions are moderate, then this rate outperforms the existing results. And also, I'd like to present some. I'd like to present some PEC and best time identification performances. So when we do arm elimination things, when only one arm left, we can declare it. Our algorithm can declare it as a optimal best arm. And this theorem tells us that when t exceeds some sample complexity, then our algorithm declares the best arm, correct best arm with high probability. And also, when t exceeds some sample complexity, then the policy has some PEC property. I think this is some favorable sample complexities, but some limitations and some future direction is, I'm not sure these sample complexities are minimax optimal when the instances are given. So it can be some limitation or future direction. Okay, thank you very much for your attention.
So I have one. So your styling is harder than linear bandits, but in linear bandits there are also this instant dependent bound that have, the optimal constant one in both the regrets and the best arm identification. Is there hope to derive such type of lower bound and matching algorithm in your setting as well?
For regret bound, I think it is optimal since we achieve dt, but for constant, I'm not sure. But
No, I mean the one with the gap. You have the distribution dependent bounds.
I think that is crude.
Yeah,
I'm not
but
sure.
Do you think if there is a lower bound log t multiplied by something, like in this end of optimism paper for linear bandits, or?
I think it matches some result of linear bandit case, since this is my conjecture, but I'm not sure how to do it. But I have some doubts about it. Yeah.
Other questions? Okay, if not, thank the speaker again. Okay, so now it's time for a little break and some apple eating. So please.
Okay, yes. Okay, hi, so yes, this is a joint work with Zachary Chase on deterministic apple tasting. So what is apple tasting? Apple tasting is a very slight modification of the standard online learning setting. Let's go over it for a minute. So we have a repeated game between a learner and an adversary. We have a domain of instances, the binary label set, and a concept class of functions from the domain to the binary label set. And in every round, the adversary chooses an example, a labeled example, but it sends only the instance to the learner, and then the learner predicts whether it's 0 or 1. And it suffers loss if it makes a mistake, the 0-1 loss. And this is the modified part. If and only if the prediction is 1, it gets the true label from the adversary, otherwise it gets nothing. Okay, so this is also called apple tasting feedback. So what we're interested in is, as usual, the minimax optimal mistake bound, which is just the expected number of mistakes. And we denote it with m star of htk for a randomized learner and m star d for a deterministic learner, where k is the number of mistakes that the best hypothesis in class makes. So when k is 0, we are just in the realizable case. Okay, so this is the setting. Now, why would we care about it? So apple tasting is supposed to simulate scenarios where we want to separate the instances into two types, usually good instances and bad instances, where one of the types is for some reason gets disappeared after the prediction and we can't really verify the outcome. So there are many such scenarios we can think of, and one example is just literally apple tasting. So think you want to sell apples and you want to only send the good apples to the market. So once you decide an apple is good and you send it to the market, you can't taste it and really verify that it's good. But the bad apples that you keep for yourself, you can taste and make sure that they're actually bad to improve your next predictions. Okay, so if I convinced you that apple tasting is important or interesting, so we can now ask, but why deterministic apple tasting? Because we have perfectly fine randomized apple tasting learners like Feinbold et al. From 2000 and from Rahman et al. From Colts last year. So why would we care about deterministic such learners? So actually there are many reasons. First of all, for example, so deterministic bounds hold with probability 1. We have complete certainty. It's not just in expectation. They hold against an adaptive adversary because there's no point in being adaptive when the learner is deterministic. There's just nothing to There's nothing to adapt to. And we don't have to worry that our randomness generation mechanism might get exposed just because we don't have such a mechanism. And at least in my opinion, maybe most importantly, is that deterministic learners are usually fundamental and natural in the sense that they use some core structure of the problem. And famous examples are SOA and weighted majority. Okay, now if I've convinced you that this is all interesting, then we can talk about the results. Okay, so we know that the optimal randomized mistake bound is at most something like order of square root Littlestone t. From 2000, Littlestone of the class, of course. And in Colt last year, Rahman et al. Asked if we can get a vanishing mistake bound with respect to t, also using a deterministic learner. So we show the following more general positive result, that the deterministic mistake bound is at most order of square root t times k plus Littlestone log t. And of course, this gives as a special case a positive answer for the realizable case. And we also give a lower bound showing that this upper bound is actually exactly tight up to constant factors for some classes. And of course, this gives also as a special case a lower bound for the realizable case. And interestingly, last year in the Colt paper, Rahman et al. Gave a randomized upper bound of k plus order of square root Littlestone t log t. So I want you to note that there are significant gaps between the randomized and deterministic learners. So even in the realizable case, we have this square root log t difference. And in the non-realizable case, it is much more significant. We have a deterministic lower bound of square root tk, and a randomized upper bound of only k plus square root t as two different summands, which can be really large for some specific k values, for a lot of k values. And I just want to know that this is actually a known phenomenon in partial feedback settings, this gap between randomized and deterministic mistake bound. For example, we have a paper last year showing that this happens also in bandit feedback setting. Okay, now to talk briefly about the technique, I want to state a much more simplified setting of realizable experts to demonstrate a bit the techniques. So forget about function classes, forget about instances. We just have n entities called experts, and those experts freely making 0 or 1 predictions adversarially in each round. And we even have a perfect expert that completely realizes the true labels. So we're in the realizable setting. And we can, in this simplified setting, ask for the randomized and deterministic optimal mistake bounds. So what are the mistake bounds we have? So from 2000, we have this tight mistake bound of square root t log n over roughly square root log t. And in this work, we show a tight mistake bound of square root t log n. So there's again this gap between randomized and deterministic. And I want to talk briefly about the technique of the deterministic upper bound. So to do that, let rounds of I be the number of rounds where expert I predicts 1. Of course, as long as it's still in the game, as it didn't get eliminated by being inconsistent with the feedback. So let's consider two very extreme and easy adversarial strategies, but we start with those simple strategies. So in the first strategy, we have just a single expert predicting 1 in every round. So in this case, if you think about it for 2 minutes, you'll see that a good strategy for the learner is to predict 1 once the round's value of some expert reaches square root of t. And if you think about it for another minute, you'll see that this guarantees at most square root t mistakes for this specific easy strategy. Now, also note that for this strategy, the adversary wastes a lot of rounds, like square root t many rounds, on every learner's mistake. So this is one extreme. So if this is one extreme where a single expert predicts 1, the other extreme, the other possible adversarial strategy, which is extreme, is that most of the experts predict 1. Let's say even more than a half of the experts predict round in every round. So this is even more obvious even that a good strategy here is just to predict 1 every time and eliminate half of the expert every time. And then this guarantees at most log n many mistakes. Okay, and in this case, the adversary just spends 1 round on every mistake of the learner, but it wastes a lot of experts. So in the first extreme, it wastes a lot of rounds, and in the second extreme, it wastes a lot of experts. And we can handle both of them pretty good. So the challenge lies in the fact that it's not obligated to use, of course, one of the strategies, can do a lot of interesting and hard stuff in the middle. So how can we handle this? We just interpolate pretty much between the easy cases and predict 1 when a weighted sum of the experts predicting 1 is large, where the weight is a function of the number of rounds wasted on this expert. So technically, we implement this by using exponential weight. So the weight of I is exponential in the rounds number. And if we do a technical analysis, we have a mistake bound of something like log n over eta plus t eta for every eta and for every adversarial strategy. And if we choose eta correctly, we get the square root t log n mistake bound. And now I want to conclude with an open question. So let me quote like a few sentences from the previous slide. So we said we use an exponential weights forecaster, and we had this log n over eta plus t eta, and we choose eta and get this square root t log n mistake bound. So this probably sounds familiar to some of the people in this room. And indeed, this is a screenshot from the famous prediction learning in games. This is one of the first results in this book, given a regret bound for the most basic full information expert setting. And here we also have the exponentially weighted forecaster, and we get this exact same expression with this any eta. And this raises a natural question of whether this randomized, non-realizable, full information, standard, well-known expert setting is in some sense related or even somehow equivalent to this deterministic, realizable, apple-tasting expert setting. And that's all I have. Thanks.
Thank you. Do we have questions?
Like that's kind of related to the last question that you were asking. So I was wondering, like this new kind of feedback. If you
Should I get?
yeah, this thing. So I was wondering if you can generalize this to a much more general settings like linear bandits and all, and if there's an analog version of any question in that space.
Okay, I don't know if there's an analog in linear bandits, but
Yeah.
I think trying to generalize this is an excellent question. Like maybe there's a more general setting somehow integrate both in a way that gives you like a framework to analyze all kinds of those settings, that would be very nice. Thanks.
Okay, so our next speaker is Justin, who will speak about causal calibration.
Cool. Yeah, it's nice to see everyone. As was said, I'll be talking about causal calibration today. And so this is joint work with Chris Chung at Meta, Vasilis Serkanis, Brian Wilder, and Stephen Wu. And so before I dive into the formal problem statement and our results, I sort of want to talk about what is calibration, what is causal inference, and sort of how do these two topics sort of interplay with one another. So first of all, I'll start with calibration. What is calibration? So classically, one would say that some model predicting a regression function, the expectation of y given x, is calibrated if for any prediction the model can make, the expected outcome conditioned on this prediction is just the prediction itself. More broadly, suppose we have a model predicting the conditional minimizer of some loss function L, then a natural notion of calibration is as follows. It says basically the expected partial derivative of the loss with respect to the first argument, or the prediction, given any value of the prediction, is just equal to 0. This recovers the first notion of calibration for squared losses, and semantically it makes a lot of sense. It says that a model theta is calibrated if, given the current level sets, there's no way I can update the value of the prediction to further decrease loss. Why do we care about calibration? I'll just do like a simple graphical example. Suppose I'm a doctor, I have a model that predicts the probability someone will develop a disease, and I'll give them a treatment if that probability is bigger than, I don't know, 25% seems kind of high, but let's say 25%. Then, if my model's miscalibrated, and maybe when it predicts I will not develop a disease with a high probability and half of the people do, we might run into trouble. And so this is very heuristic, but one can actually show that if I'm a decision maker and I'm equipped with calibrated predictions, then the best thing I can do to maximize my expected utility is to directly leverage the model's predictions. How does this relate to causal inference? Well, a variety of causal effects are naturally used in everyday decision-making tasks. I'm going to go through a couple examples here just to give some sort of sense. So let Z be a triple XAY, or a generalized observation. We'll work in a potential outcomes framework, which means for any possible treatment, there's a random variable YA representing an outcome, and we always observe the outcome with the associated randomized treatment. I'll do a couple examples. So in the treatment's binary, we might be interested in something like a conditional average treatment effect, or CATE, which is just the expected difference between treatment and control conditioned on the covariates. Likewise, perhaps my treatment is continuous, perhaps it's a dosage of a medicine. I might be interested in something like an average causal derivative, which is basically just the expected change in an outcome given an infinitesimal perturbation to the dosage. And so naturally, if I'm a doctor, I might want to use one of these two things in deciding whether or not to give someone a treatment if I think they might be susceptible to some disease. And given what we know about calibration, since these causal effect estimates are being used in decision-making pipelines, we should ensure they're calibrated. However, this is where we reach somewhat of a problem. Almost all calibration algorithms require what I'm calling full observations. What does that mean? Algorithms like isotonic calibration, histogram binning, even something simple like Platt scaling, all involve regressing observed outcomes, y1 through yn, onto the predictions of a model. This gives us a post-processing that guarantees, at least as I get many calibration samples, I can put this on like the end of a model and it will make it calibrated. However, even in the simplest setting where we have two treatments, a control and maybe the application of a medicine, we only ever observe one outcome, never both. Moreover, because of this, it's sort of non-obvious how to extend these sort of typical calibration algorithms to a causal setting. And this will bring us to our goal. Surprisingly, very little work has been done on calibrating estimates of heterogeneous causal effects. I would like to point attention to one sort of work that was the inspiration for our work, which was by Lars van der Laan at University of Washington. And what they show is that one can use a specific calibration algorithm, isotonic calibration, to calibrate estimates of conditional average treatment effects. And so it's a really great result. But people have been studying calibration algorithms for years, and they've, for each calibration algorithm have derived a variety of convergence guarantees. Likewise, depending on sort of the decision-making task at hand, we might be interested in effects beyond just CATEs. We might be interested in these causal derivatives, quantiles, or other things of the sort. So that brings us to our goal. Our goal in this work is to develop a framework for sort of calibrating any causal effect you can think about using your favorite off-the-shelf calibration algorithm. And so this sort of sets the stage. Now we're going to spend some time formalizing the problem. Okay, so first of all, what is a generalized causal effect? So here we're going to specify a causal effect, theta 0 of x, as conditionally minimizing some loss function L. And so the loss function L here is a bit more general than the one we saw earlier. It basically depends on a prediction denoted nu, an observation z, but now also a nuisance component, g. What is a nuisance component? It's in general a high-dimensional function that allows us to informally debias observations to make them look as though they're fully observed. And so theta 0 of x is the conditional minimizer of this loss function when I plug in a true unknown nuisance function, which depends on some subset of variables. Then, once we have this model for theta 0 of x, we simply say that theta of x is calibrated if, once again, the partial derivative of the losses vanishes on any level set. And so how do we measure calibration error? Well, given finitely many samples, perfect calibration is impossible, but instead we can consider a natural L2 variant of calibration error. What this means is we just average over the level sets of the predictor the squared deviation from the perfect calibration condition. And so our goal is, given, let's say, n samples from the data generating distribution, some initial estimator theta of x, we want to output a theta hat of x such that the calibration error is small. Maybe it's inverse polynomial for some gamma. Okay, and this takes us towards our results. And so in the paper, we handle general losses, and I'm happy to talk about that offline, but for the sake of exposition, we're going to look at slightly simpler losses. We'll just look at losses that just look like squared losses, but where we replace the outcome y with something called a generalized pseudo-outcome. What is a pseudo-outcome? It's basically something that depends on the generalized observation and the nuisance component that is conditionally unbiased. Well, when I have the correct nuisance component, the conditional expectation of this thing is the effect I'm estimating. And it's also sort of insensitive to misestimation in the nuisance component. That means if I take a directional derivative with respect to the some perturbation delta in the nuisance component, when I plug in the true nuisance component, this thing vanishes. Then for this restricted setting, calibration has a very natural notion. It just means that the expectation of the causal effect, given the prediction is p, is also just p. I'll just sort of quickly skim through one example for the sake of time. But suppose my nuisance components are like the regression function of y given x and a, and then the propensity score. So the probability I get treatment given my covariates. Then this is the standard sort of doubly robust pseudo outcome from causal inference. The first term specifies the causal effect. If I plug in mu0, it's just the Kate. The second term serves to debias and guarantee orthogonality. Okay, and so one of our main results is the following. It says if I have any loss, in the case of this presentation, a loss of this form, then for any theta hat and g hat, I have the following bound on the calibration error. Well, the calibration error of the model under the true nuisances, which is what we care about, is bounded above by the sum of two decoupled terms. The first one is sort of an error term that measures the distance between g hat and g0. The second one is the calibration error under the learned nuisance, g hat. And so what that means is we pay an upfront price for estimating the nuisance component. But then after we've done this, we can pretend we're in a world where the learned nuisance is actually true. In a sense, this puts us into a non-causal setting. Diving into a bit more details, the error term, well, if my nuisance component looks like something like a tuple, let's say eta 0, zeta 0, my estimate is eta hat, zeta hat, then the error actually gets bounded quite generally by something nice. It generally looks like the L2 norm of the product of the errors. And so under like mild assumptions, maybe that the eta 0 and zeta 0 are bounded, then if I estimate each of these in L2 norm at n to the minus 1/4 rates, then my error will actually be quite small. And the faster you estimate these things, the faster the error will go to 0. Likewise, we can interpret the calibration error. So we can write down the calibration error for this specific case as, again, an average over the level sets. But here it's the difference between theta of x and the conditional expectation of something I call y hat given theta of x. Y hat is just the pseudo outcome, but the idea is this, at this point, this can be fully computed, and we can treat it as an actual observation. And so what that means is, well, we can just regress y hats onto the predictions of the model to do calibration. In particular, if the y hats are bounded, I can run something like histogram binning to get a calibration error of, I don't know, something on the order of n to the minus 1/2, or I could use isotonic calibration to get something on the order of n to the minus 1/3. And so this sort of general theorem leads us to a very simple algorithm for performing causal calibration. Given, let's say, 2n samples and initial estimator theta of x, I take my data set, I split it into two pieces. On the first piece, I use my favorite black box learner to estimate the unknown nuisance component. Maybe I run gradient boosted trees, or I use lasso or something like that. Then, once I've estimated G0 and I have this estimate G hat, I can simply compute the pseudo outcomes on the other half of the data, and then I can use whatever calibration algorithm I want to regress the y hats onto the thetas. And so I guess I'll quickly go through some takeaways. The idea is basically that we have a plug-and-play approach for doing calibration for general heterogeneous causal effects. You pass me your favorite nuisance estimation algorithm, your favorite calibration algorithm, and I can calibrate any causal effect. And so I want to point to, in this paper, we only, like in the presentation, we only talked about squared losses, but in the paper we handle more general classes of losses, but this requires introducing like some technical conditions that's maybe not best suited for a talk like this. Yeah, that's it.
We have time for questions. Okay, so maybe you can tell us a bit more how you manage to combine really any choice of estimator on any calibration, like.
Yeah, so I can, let's see, I think this thing will scroll back a bit.
It's due to this decomposition that you.
Yeah, so I'm not going to scroll back all the way, but it's basically due to the fact that we ensure the loss is robust with respect to the nuisance component. So the directional derivative of the loss vanishes. And so any error we pay in terms of nuisance estimation is second order in nature. So we'll have like squares of terms, but that's generally quite small. And so once you've done this, all that remains is the sort of calibration error under the learned nuisance.
Yes?
And you mentioned some causal derivative effect. Then in this case, for derivative effect case, the nuisance estimation is the nuisance estimator of derivative of the.
So the nuisance estimate you can still take to be the regression here. And that's like a nicer way to do it. But then you would have in your estimating equation, or sort of the way you'd write down this effect, you'd have the derivative of whatever your estimate is. So you'd have to use some sort of like smoothed estimator to approximate it.
Okay, thank you.
Okay, in the interest of time, we will move on. Thank you. Okay, so our next speaker is Steve. The floor is yours.
Thanks. Okay, so I'm going to talk about multi-class learning with bandit feedback. Suppose, just a motivating example, suppose we're some scientists and developing some treatments for illnesses, and we get some like N IID patients coming in, and for each one we can design some kind of chemical compound that we administer as some potential cure for their illness. And we just see whether it cures them or not what would have cured them. And we can only treat each patient once. And then let's say after we experiment on N patients, our goal is to produce some function that would map future patients' symptoms to some chemical compound that might cure them. So we can model this as a problem of pack learning with bandit feedback. And then the question is, how should we design a learning algorithm for this problem? But of course, there's potentially an infinite number of different chemical compounds, so that's an infinite label space. And if we look at the pack literature on bandit feedback, it says, well, if the label space is infinite, it's just not learnable. So it's not possible, don't even try. But just because some paper tells us it's not possible doesn't make us stop wanting to solve this problem. So the point is we have to turn to other perspectives if we want some kind of theory that would inform how we should design our algorithms. And in this work, we look at the universal rates perspective, and we find there's a perfectly reasonable theory there that gives rise to interesting algorithmic principles, and moreover, we derive optimal rates. So just to introduce things formally, learning problem here is a distribution P on XY pairs, where X is an instance space, Y is a label space. Here we'll suppose that's at most countably infinite. In supervised learning, you would get N XY pairs drawn IID from the distribution P, and then your goal would be to produce a classifier, just a map from X to Y. In the bandit feedback setting, it's a little more involved. You don't get to directly observe the Ys. Instead, you go through your n examples one by one, and you guess a label, and you just get to see whether you're correct or not. So you don't get to see the true label, just whether your guesses were correct, and you only guess once per example. But still, the goal is to produce a classifier. And of course, what we're interested in is having a low error rate under the distribution P. So error rate is just the probability that you're wrong on a fresh xy drawn from the distribution. The structure of this problem comes from supposing we have a concept class, H, which is just a set of classifiers, functions mapping x to y. And in this work, we'll restrict to the realizable case. So we'll always suppose we're just looking at distributions where the infimum error rate in the class is 0. And then what we're interested in is understanding what are the possible rates of convergence for the expected error rate. In the classic, the uniform or minimax or PAC analysis, for the best algorithm in the worst case over distributions for a given sample size, the expected error is characterized by two things. One, the Notarian dimension of the class. That's a generalization of VC dimension to the multi-class setting. And two, the effective size of the label space. In particular, if you have an infinite effective label space size, the PAC theory just says it's not learnable. And as I said, we'd like to have a theory that holds even when the label space is infinite. So we'll turn to the universal perspective. So rather than studying the convergence of the max over distributions of the expected error rate for a given sample size, where that max might be witnessed by different distributions for different sample sizes, we'll instead look at the rate of convergence of the expected error rate that can hold for all distributions. So the sort of nuance there is that we're just looking at asymptotic rates, so you could have distribution-dependent constants. So for instance, as in the picture, you could have a rate that's like e to the minus n times a constant that depends on the distribution, and that would count as an exponential rate. And we find there's a very reasonable theory for this multi-class with bandit feedback in the universal rates perspective. In particular, every concept class falls neatly into one of three categories. The optimal rates can be either exponential, 1 over n, or can require arbitrarily slow rates. We also give combinatorial structures that distinguish which classes are in which category. Class gets exponential rates if and only if there's no infinite Littlestone tree. The 1 over n rates happen if and only if the class has an infinite Littlestone tree, but neither an infinite Notarian Littlestone tree nor an infinite progressive Littlestone tree, which are two structures I'll define in a bit. And otherwise, it has arbitrarily slow rates. I'll try to focus most of the talk on the 1 over n upper bound rate, which is kind of the most interesting one algorithmically. It actually reveals some interesting connection between the bandit feedback setting and the list learning problem. Okay, let's talk about those structures. So the simplest one is Littlestone trees. So an infinite Littlestone tree is just an infinite binary tree where the nodes are labeled by x's from the instance space, and the two edges have labels from the label space, where two siblings have to have different labels. We say a class has an infinite Littlestone tree if there's an infinite perfect tree of this type, such that for every finite depth path from the root, there's a concept in the class that's correct on all of the examples on all of the edges along that path. And we show any class is learnable at an exponential rate if and only if it has no infinite Littlestone tree, and otherwise, at best, 1 over n rate. For the sake of time, I'll skip this. I want to talk mostly about the 1 over n upper bound, so yeah, feel free to ask offline. Okay, getting toward that 1 over n upper bound, let's talk about the two structures that are relevant there. The simplest is the progressive Littlestone tree, which is defined just like a Littlestone tree, except the nodes at depth k minus 1 have k children. And again, all of the sibling edges have to have different labels. So you get larger and larger branching factors as you go down. And again, a class has an infinite progressive Littlestone tree if there's an infinite perfect tree of this type, such that for every finite depth path from the root, there's a concept in the class that's correct on all of the examples on all the edges along that path. The reason this is interesting for us is because we show if there's no infinite progressive Littlestone tree, then there's a supervised online list learner, meaning that if you run this algorithm on any infinite sequence of xy pairs realizable by the class, after a finite number of rounds, it will produce a list predictor, meaning a function that maps x to some list of some number k of labels, such that for every xy pair in the sequence, if the label y will be in the list produced by applying the predictor to x. So you can kind of capture all of the labels. So think of this as a way of maybe we started from an infinite label space, but this list predictor gives us a way to boil down to a finite label space. The other structure is the Natarajan Littlestone tree. So this is defined just like Littlestone trees, except now the nodes at depth k, instead of one example, they have a k tuple of x's, and they have 2 to the k outgoing edges labeled by the 2 to the k labelings that would witness a Natarajan shattering of that k tuple. The reason this is interesting is because if a class has no infinite Natarajan Littlestone tree, then there's a supervised online partial concept class learner, meaning that if you run this learner on an infinite sequence of xy pairs realizable by the class, after a finite number of rounds, it will produce a partial concept class of a finite Natarajan dimension for which the xy sequence is also realizable by that partial concept class. So think of this as a way that even if your original class had infinite Natarajan dimension, running this, it will produce a partial concept class for which has finite Natarajan dimension and for which the sequence is still realizable. Okay, so the way we're gonna try to put these together to make an algorithm that gets the 1/n rate, I'll first describe something that doesn't quite work, and if there's time, I'll say how to correct it, but this is the basic idea. We have n IID examples. Let's split them into 2 parts of n/2 each. In the first part, let's just randomly guess labels according to some distribution that has full support on the label space. And just keep the examples we got the label correct. So this way we have a supervised labeled data set. And then we'll run our 2 online learners through that to get a list predictor and a partial concept class of finite Natarajan dimension. Use the list to prune the partial concept class, the partial concept supports to just the labels that are actually in the list. So what we get out of that is a partial concept class, finite Natarajan dimension, and finite effective label space. And then we use the other n/2 examples to do some supervised learning. I guess first we have to guess some labels, so we'll use our list again, guess randomly in the list, and we'll get about a constant fraction of them correct. And then just run a supervised learner for the partial concept class on that, and it gets like this kd log k/n, where k is the size of the list, d is the Natarajan dimension of the class. If you're familiar with this literature, you know this doesn't quite work, but we can apply some usual tricks where in the first n/2 examples, let's first break it up into some batches, apply the same idea to each batch, and just aggregate to the list predictor and majority vote predictor at the end. Thanks.
Time for questions. Yes.
In your theorem, by the lack of an infinite 2 types of Littlestone trees, you're meaning that there is no tree, a single tree of infinite depth instead of like an unbounded finite Littlestone tree of 2 types.
Absolutely, yeah, an infinite tree, and that's an important
and that
distinction.
implies the universal bound.
Right, yeah. So you could have classes that have unbounded finite size trees of those type, but if there's no infinite tree, then you still get the rates.
All right, thank you.
Another question? I have one just out of curiosity because I'm not an expert of all this, but on one of the first slides, you said that you were considering a new definition where your rate could depend on some function of this p, the prior. So where does it show up in your result in the end?
Right, so can I go back? Yeah, so for instance, like this K and D, we ran something on data and it produced a partial concept class. The dimension of that class will depend on what data we run it on. Also, the size of the list K, that's also going to depend on what specific data we run it on, and that's going to be informed by the distribution. So these constants, and maybe
Okay,
also sort of how big n has to be before this rate kicks in. These
Okay.
things, this is where distribution dependence comes in.
Thank you. Okay, thank you, the speaker again. Okay, so our next speaker is Arnab. The floor is yours.
Hello. Yeah, cool. Yeah, welcome to this talk on online shortest path in directed acyclic graphs. And this is a joint work with my collaborators at MIT and Washington. Okay, like I'm considering a very classic bandit learning problem, like where you are given an input graph, which is directed acyclic graph. It has like two nodes, like one of them is like source node and one of them is the sink node, which is of importance to us. So in each round T, an adversary shows up and assigns losses to the edges in an adversarial fashion. And we as a learner, we have to choose a path from source to sink. And we incur a total cost of some of the losses of the edges, and we only observe this particular loss as the bandit feedback. And the goal is the standard regret minimization, where you want to minimize regret with respect to the best path in hindsight. So just few mathematical notations. For example, I'm using calx to denote the set of all paths from source to sink. And I'm also going to represent the path using a vector x, which is indexed by both vertices and edges. You'll see why I did that later in the talk. But essentially, like for any vector x, x of v is 1 if v is part of that path, and similarly, x of e is 1 if e is part of the path. And it's kind of well known that the convex hull of the set of all such paths forms a flow polytope, and efficient implementation is known over such paths from a pure optimization perspective. So mathematically, like we as a learner have to choose a vector xt, and an adaptive adversary will be choosing a loss vector yt, and we as a learner will observe the inner product xt yt as our loss. And just like a small note, like the vertices actually don't have any loss, it's just for notational sake. And yeah, the goal is to kind of minimize the regret with respect to best path in hindsight. Yeah, and this is also like a typical standard assumption where you assume that loss of any path is kind of bounded between -1 and 1. So what is known in this space? You have the standard exponential weights algorithm, and in this talk I'm more interested in the high probability version. So yeah, there's a high probability version of exponential weights that achieves like a regret of square root dt log cardinality. So for DAGs, like d is essentially the number of edges. And exponential weights is kind of known to be minimax optimal for this problem. But what's the issue with exponential weights? At least for this particular variant of the exponential weights, efficient implementation is kind of known. So the question that we are interested in is like, can we get the same regret bounds as exponential weights, but by constructing a computationally efficient algorithm? So before even we try to answer that question, like we can take a step back and ask, like, okay, like where are the places where we can improve, especially if we don't want to just come up with another variant of exponential weights. So one place where we can improve is directly at the loss estimator place, where typically in the literature, like folks try to like construct the estimator such that it is unbiased, but the question is it like necessary? And the answer is no. Like, what you actually require is, like, if you take any two paths, x and x prime, the difference of their estimates should be actually unbiased. And this is what suffices. So a key contribution of our work is actually a new estimator for DAGs. And for the simplicity of presentation, I'll just assume like the number of edges on any path from source to sink is k. So a key part of why our estimator will work is that we'll be doing like Markovian sampling. So essentially, if I reach a particular node V, then the probability with which I'll choose the next node E will not depend on how I reach that node V. So this is what our new loss estimator looks like. So it's like kind of mimicking the standard multi-arm bandits loss estimator. So for example, for the edge, you have like 1 plus LT multiplied with indicator that the edge was chosen, divided by the probability that the edge was chosen. And similarly for the vertex, you have this 1 minus LT times indicator that the vertex was chosen, divided by the probability that the vertex was chosen. So this is the new estimator that we propose. And this is definitely not an unbiased estimator, but what will show that this is going to be actually difference-wise unbiased. And the key idea is kind of this, like, say you condition on the fact that you're going to pass through a particular vertex V, then what is the expected loss that you can that you're seeing? So you can kind of decompose the path into two parts, the left-hand side and the right-hand side. And so the expectation kind of splits into two parts. Similarly for the, if we condition on the fact that we are passing through an edge, then it kind of splits into three parts. So the left-hand side, the middle edge, and the right-hand side. And so like your expectation on the condition that you're going to that edge splits into three parts. And this is where the Markovian property kicks in, because I can just replace the conditioning on edges by the corresponding vertices. And then, just to recall, for the edge part, you had a plus, and the vertex part, you had a minus. So roughly what will happen is that when you traverse along a path, the extra terms will kind of cancel out each other. And you'll be left with this, just the sum of the edges on the path, plus this extra ones that is there. So those extra ones will kind of add up to be the number of ones, essentially. As a number of the length of the path, and I assume that the start they are same. So essentially you'll get that the difference-wise, this estimator is unbiased. And then you can just use this estimator and plug it into the standard FTRL algorithm. And the good thing about this is that you can use any regularizer here. And so we use like Salis inf, and we get like square root k et upper bound. And so this holds only an expectation, but you can like implicitly bias your estimators and get a high probability regret bound. And you can relax the assumptions on equal path length by kind of modifying the representation of paths, like introducing few extra bits. And then if you recall, like the regret bound was just square root k et, but k can be really huge. So another key contribution of our work is that we take the original DAG and we construct an equivalent DAG such that doing regret minimization on this is kind of equivalent to this. After doing the transformation, we can ensure that the length of the longest path here is like log cardinality. So when we plug this back into our original regret bound, we get like square root et log cardinality. So we kind of recover the minimax optimal bound. So this work kind of leads to like these three open questions. Like one, is this approach like kind of specific to DAGs, or can you extend it to arbitrary combinatorial sets? The reason I'm interested in this is because there are some works done on large iterate convergence in just like standard zero-sum games, but if we can extend this approach, that would mean like in several other combinatorial games, you can get like large iterate convergence. And similarly, like in classical multi-arm bandits, you have like best of both world results, which makes use of Salis, inf, log barrier. So now that we can use different regularizers, can we get best of both world guarantees? And something that I kind of skipped, but while we came up with this particular approach for few specific sets, we could actually improve the known regret bounds, like the bounds that was even achieved by exponential weights. So that also raises a question, like if you give me a specific combinatorial set X, how does the optimal regret scale with respect to the geometry of this set? So thank you, and open to more questions. Yeah.
Thank you. So I have one question on the computational side. So you have a new estimator that is specific to DAGs that then you're plugging and follow the regularized leader. But how is you still have to optimize something over all paths? No? Like in your, if you show your FTRL?
FTRL was somewhere spent, right? Yeah. So
for the argmin there, you have an efficient...
because the efficient optimization algorithms are known for convex hulls of paths, like because it has strong separation oracles and all.
Okay, for any function.
Yeah, for any function.
Not just linear.
Yeah. So ideally, like you don't have to compute the exact minimum. You can be approximately close and still like recover the same bounds. So
okay.
Yeah.
Thank you. Any other questions?
So could you just
That's a good question. That's also something I've been thinking about, like whether you can extend this approach to dynamic programming problems. Yeah, it's an open question.
Okay,
yeah.
Cool, thank you.
Anyone else? Okay, well, thank you again. Okay, so Jan is going to give the next talk. Please go ahead.
Yeah, thank you for the introduction, and thank you guys for being here instead of the language model session. So I'm going to talk about non-monetary mechanism design, and it doesn't obviously have something to do with Bandits causality, so I adjusted the slides to make it very interpretable, I promise. So the central challenge is something that is really classical. You consider you have an indivisible item. You would like to allocate this resource to a bunch of agents who might be strategic. They are not going to tell you the truth for various reasons. There are a lot of like classical examples in the literature, but let's say the code program chairs are going to have a keynote slot, and they just come and ask every participant, how important do you think your work is? I guess the 100% response going to be like, the responses which says 100% important is going to be dominating. I don't know. So to formalize, we consider the case where there is a planner and a bunch of agents. Every agent is going to privately receive some utility, and it is only available to themselves. And what they submit is something we call a report, and we denote it by V to distinguish from the utility U. So this V can be strategic, and the planner can only make the allocation based on these strategic reports. And the question for the planner is that how do you ensure two objectives? The first objective is efficiency, saying that you need to really allocate this stuff to the agent who is mostly in lead. And the second objective is that how do you incentivize the agents to tell the truth? And these two objectives are like interdependent on each other. So without incentive compatibility, if everyone just report 100%, then there is no way you can make an efficient allocation. So what is the existing methods in the literature? There is something very classical like decades and decades ago called VCG mechanism. It says that let's run in this specific setup, let's run an auction. And then the winner is going to pay something to the central planner, and its calculation is determined as the second highest bid. But the issue is that money isn't everything. So like, it sounds sketchy saying that let's run an auction to decide who will be the keynote speaker. And so there were some very recent works in these couple of years considering like, is it possible for us to get rid of money? No, it is a very classical topic, but there were some very recent advances. So these advances are, some examples are like, let's say that all the agents' utilities are sampled from some known distribution. Then based on this known distribution, we can allocate some budget to all the agents. Or we can promise the agents that if you're honest, then I promise that you can get what you're like entitled to. And these approaches heavily rely on the knowledge of this distribution. But the thing is that distribution information is also not really usually obtainable. So for the code case, it is probably yes, because we are in a small community, but there are many other examples where it doesn't really hold. So our question is that what will happen if there is no distributional information as well? And can we just get rid of any prior information, but instead we try to learn something in this interaction process and to ensure efficiency and also incentive compatibility? And the answer is that we design something that allows the planner to, this is the model setup. So we assume that the planner can sometimes choose to audit the winner, and this audit will reveal the winner's true utility. In this case, if the planner audits the winner agent 2, the agent 2's true utility U2 will be available. So the question is that how many audits are enough, or like in a more theoretical way, what is the sample complexity? But yeah, it is not really equivalent to sample complexity, as we will see shortly. So now there is a trade-off for the planner. First of all, we would like to minimize the social welfare regret, which looks really similar to online learning regret, but I have to mention that they are very different. In online learning regret, what you are competing to is, in static regret, you compete to a fixed comparator. In dynamic regret, you also compete something that is fixed before the start of the game, but now you're competing with the hindsight optimal, which might depend on the realization of these utilities. So, and why it is doable is because you have some reports, so you have much more pre-decision information than in online learning. And the second thing that the planner would like to trade off is the expected number of audits. So if you always audit throughout the game, and agents are naturally do not dare to lie, so you can for sure ensure a very good regret, but it doesn't really make sense because audits are like, in realistic world, it is also costly. In our model, it is for sure also more expensive. So our main results saying that, okay, first of all, we get a baseline, which is basically saying that, okay, if you just audit every single round, then you can get very good regret, which is independent to T. And instead, if you almost do not do any audit, then you will suffer a T regret, linear, super bad. And there is a trade-off saying that, okay, you can do a linear interpolation, and the best case is that square root of T and square root of T. But this is not super interesting, as we managed to design something that is really far away from this baseline approach. We designed something called ADA audit, and it achieves a constant regret that is completely independent to T, and also it only uses a logarithmic number of audits. And we also complement with some like impossibility results, saying that first of all, you cannot hope for zero regret. Second, you cannot hope for zero audits. And okay, cool. We managed to have 5 minutes for a one-slide technical overview. So the first step is that because of the audits, we are able to impose some type of threats. We threat the winner, we threat all the agents that if you win and I audit and I find that you are lying, then you are eliminated for all. I will never allocate to you again, no matter how much you are reporting in the future. So this is something that is threatening, but as we already see, we can only afford a logarithmic number of audits. So the problem is that how do we adaptively allocate these very like scarce audit resources? And it is not super hard to design something assuming the full full access to the true distributions, that if your audit probability is inversely proportional to the agent's expected gain if they are staying alive in the future. So this is basically something called fair share in the mechanism design literature. And if you already know this fair share and you tune the audit probability accordingly, then you can ensure that agents are almost never dare to lie unless they have, like, for example, they have totally no hope of winning, then lying ones at least give you something. So in this case, you can ensure that the regret is going to be constant, and the number of audits is only going to be logarithmic. And I gave a one-sentence comparison, like just your agents will carefully think about two possibilities. One is truthful and secure everything in the future. Second is that you get something immediately, but you lose a lot in the future. So the thing is that we do not have the distributional information, so we cannot actually know this fair share. So the issue is that how do we really learn in a strategic environment? So this fair share is really related to how many times that the agents are going to win. And let's pretend for now that all the agents are already super truthful. Then one very natural idea is that, okay, let's just do a empirical mean, and if we are, because you can see it's a proportional stuff, so we only need a multiplicative approximation. Now in this case, we cannot really conditioning on a good concentration. It's because if some agent feels that, okay, there is a huge chance of the estimation is eventually wrong, they will strategize early so that everything just breaks. Our idea is that that's the agents to flag each other. We tell the agents that if you think someone else is like gaining an unfair advantage, then you tell it to me, and I will redo something to ensure that they're back on the track. This aligns the agent's incentives with the social welfare incentive. And another challenge is that there is something called revelation principles in mechanism design, saying that you can always, without loss of generality, assume that truthful is a equilibrium for all the agents. Oh, the PBE here is a notion of equilibrium. But here it is not applicable because of some reasons that is not easy to say right now, but you can ask offline. So our approach is that let's consider defining a well-behaved auxiliary game, and we prove that every equilibrium in that well-behaved game is also equilibrium in the actual game. So this approach gives us the existence of a well-behaved equilibrium in the original game as well. And putting all this together gives our main results as displayed on the left. And the right-hand side is the technical ingredients in our paper. We show that for resource allocation, even without money and without prior distributional information, you can still gain some very good results based on some learning and based on some like very careful planning. And thank you very much. Here is the link for the paper.
Any question? Okay, so I have one. Are the agents aware of how the audit will work, or?
Yeah. So in mechanism design, the literature usually assumes that what the planner is going to do is fully known to all the agents.
Okay, and then they adjust. They know that they will be very severely
because they are fully
punished.
rational and they need to know what you are going. So it is like you design a game. So in game theory, every agent is fully known that how the game will behave, and in this case, the mechanism that the planner uses is just the game.
Yeah, okay. And how about this punishment that are really strict? If you lie once, then you will never be queried again. Would it make sense to not query for some random time for agents who hope to be again in good favor with the...
Yeah. But I mean, our overall objective is that you just never lie throughout the game because this is what we hope for. So we are really harsh on that. Okay. So yeah. And also, the more complicated the mechanism is, the more room actually allows the agents to game with it. So we need to design something that is really simple so that agents have no room to, rigorously have no other way that can game with this approach.
Okay.
Thank you.
Thank you. No more question? Okay, then let's move to the last talk of the day.
Thanks for resisting until the very end. I appreciate it. All right.
Okay, so our last speaker will be Tom on markets again.
Yeah. Thank you, Emily. So let me see how this works. If it does. Okay, good. Hello, everybody. So this is joint work with Nicola, Rob, Luigi, and Vinayak, all of which are present right now. So if this is boring, you can just play Find the Co-author in the audience. I hope it's not going to be the case. So let me introduce to this problem, this market making problem. We are a market maker, somebody that wants to increase the liquidity of the market. In this picture, we're Super Mario. We enter the market and we say, folks, we will buy some shares at some price and we will sell some shares at a different price. And of course, we always want to buy at a lower price than what we sell. Otherwise, people would just buy shares from us and sell them back to us, and we just lose money for no reason. So our market taker, Yoshi, comes to the market and has a bunch of shares and has their own individual private idea of how much these shares are worth, VT. And depending on how VT sits with respect to our bids and our ask, the amount of money that we're asking and then we're willing to pay, three things can happen. Say, for example, that the valuation is below our bid. Then Yoshi says, wait a minute. The value of the shares is VT. Let me use this. I just wanted to do this. It's not really necessary. You're willing to give me BT. It's higher. That's great. I'm going to sell. So Yoshi sells the shell to Mario. Mario doesn't want to hold on to the shell for too long. So at the end of the day, week, whatever, at the end of the time step in this repeated setting, Mario goes to the market and sells the shell to the market at whatever current market value we have today, empty. So this was case one. Case two, what if VT is above AT, above our ask? Then Yoshi says, okay, I know that the value of these shells is higher, so I'm gonna buy some more from you. But there's a bit of a problem now because as you can see, Mario has no shells with him right now because he keeps offloading the shells to the market. So Mario does something called, oh, I didn't start this. Okay, I'll just use you. So he does something that is called, it sells short. So he sells something that he doesn't have with the promise that later on, if Yoshi wants the shell, Mario will go to the market and get the shell. So Mario sells air to Yoshi, and later on, when Yoshi says, it's time to pay up, it's time to give me the shell, goes to the market, gets the shell, and gives it to Yoshi. Okay? Last option is if VT is in between the bid and the ask, then Yoshi says, you're not paying enough, you're not offering enough money for the share that I have, so there's no reason to trade, and they just walk away. Okay, so let's make this slightly more formal. This is a repeated online learning problem where at every time step, the taker, Yoshi, arrives with private valuation VT, a number between 0 and 1, say. Then the maker posts an ask and a bid with, as I said, BT always less than or equal to A. And some feedback is revealed. The feedback that is written there is just saying whether the taker is buying or selling and the value of the item, the market value of the item at the end of the day. And then the maker obtains some utility. The utility, as you see, is the sum of two terms. The utility that the maker gets when they buy something. And if you have in mind the first price auctions, you will see, let me use this again, you will see that this is the same type of utility you have when you're first price auctions. You have a utility only if you beat the highest highest competing bid. And in that case, you get some value minus what you paid. While the second term, the utility you get when you sell, is the same as what you get in dynamic pricing. In dynamic pricing, you post a price. If the price is low enough for the buyer to buy, then the buyer buys at your price minus whatever production cost, MT. So keep this observation in mind for 1 second. And the goal, as in all respectable bandit problems, is to minimize the regret with respect to the best fixed pair, in this case, of bids and asks. All right, so if we have this intuition that market making is somehow a blend of first price auctions and dynamic pricing, let's try to see if we can use some algorithmic ideas from the two problems and blend them together for our market making problem. So, upper bounds idea. Let's say that you run in parallel two online learning algorithms, one for first price auctions and one for dynamic pricing. You have to post two values, so why not doing that? And you use the recommendation of the first price auction algorithm to post the bid, and the recommendation of the dynamic pricing algorithm to post the ask. So this is an okay heuristic. The only problem with that is that we want to guarantee that the bid is lower than the ask, and this is not guaranteed at all. And in fact, it's kind of the opposite, because first price auction, they try to be just above the valuation, and dynamic pricing want to be just below the valuation. So what if, whenever this happens, they're not ranked the correct way, we just do the opposite of what the algorithms are doing? Sort of a heuristic approach. Well, you can prove that this is more than a heuristic. You can prove that this is an algorithm with guarantees, and both in the stochastic setting, so when VT, the valuations, and the market values are IAD, and also in the adversarial setting, you can get guarantees, specifically guarantees of order T to the 2/3. So there's some added assumptions in both cases. There's in the stochastic case, we're also assuming that the valuation of the taker is independent of the market price at every time step. And in the adversarial case, we're assuming some smoothness on the distribution. We're assuming that the CDF of market values and valuation is Lipschitz. So let's accept these assumptions for now, then we will rediscuss them in a second. So, question, is this rate even optimal? Maybe we could get the square root of t. Lower bounds. So, the theorem said, well, what we prove, this is by far the most technical part of this paper, is that this rate is indeed optimal, and is optimal even if you squish all the assumptions together. So, stochastic setting, IED, independent evaluations, Lipschitz, you still cannot do better than t to the 2/3. And if you try to remove one of these two extra assumptions that I sort of slipped through in the previous slide, well, the problem becomes impossible. So even in the stochastic case, if neither valuations are independent nor the joint distribution is Lipschitz, then you can prove this worst case linear regret bounds. So in a sense, they are necessary, or something else is necessary. Is to learn. Okay, so now, start the timer. So I usually take a lot of time on this because this is where the meat of the paper is. So what you see here is a picture of that sort of represents what we do in the lower bound. We build these hard instances to learn. Remember, our action space is pairs of bids and asks, is the hyper triangles. And we build them in a way where each perturbed instance of this lower bound construction has a sort of this shape. The amount of information that we get by playing a given pair is represented by the KL plot over there. And it's kind of high, see close to the, let me use this again. It's kind of high close to the diagonal. Is low but non-trivial close to the very top, which is where the reward is at its maximum. So now, if we were to just restrict the lower bound to algorithms, they play at the very top of the picture, so only at the segment where, let me show you the picture. So this is what the kind of loss and feedback that we would observe, okay? And if you look at it, and if you're familiar with first price auctions, you would say that this is the same lower bound construction that you use for first price auctions. But then you're saying, okay, fine, this is a very specific way of choosing bids and asks. What if I consider algorithms that do something else? So, and in fact, consider, for example, algorithms that play on this line. Then you see that you have a very weird shapes for both of this amount of information that you can get after every interaction and the reward. They're not both of them monotonic at the same time. They're not even univariate. This one, they don't grow or decrease at the same time. So the question is, how do you still get a lower bound that holds for any possible algorithm? And you essentially need three things. First, and most important thing, you find very good co-authors. That's crucial. The second part for this construction is you essentially do a tessellation of this upper triangle in little regions, and in each little region you control the KL divergence and you control the amount of reward sort of independently. And the third step, you try to glue all of these small estimates together and pray the math gods that the lower bound will hold. And luckily for us, it did hold. So, summary of the results. So for all the variants, I mentioned a bunch of different assumptions. For any subset of these assumptions, we have tight rates, upper and lower bounds. And two takeaway messages is one, for upper bounds, if you have problems like this, and if you have a way to see in your problems that there are some aspects common to other problems, try to use tools coming from these other problems. Maybe you cannot use them directly as us, you need some other ideas, but it will help to at least get you an idea of the rates that you can get. And the second one, if you are ever in a situation like this, when you have these nasty lower bounds, where the learner can trade off an arbitrary amount of reward to get higher feedback, maybe doing something like what we do in the paper will help you. Try to partition the space in a given amount of regions and treat each one of them separately. Okay, so this is everything. So thank you again for staying until the end.
Thank you. So, last questions of the day. Tim? Or you can shout, maybe.
I was wondering, in the upper bound construction, does it go via reduction to these other, formal reduction to these other algorithms, or do you have to intervene in their derivation?
Yeah, you can call it a reduction. So you can build two algorithms, one for first price auctions, one for dynamic pricing. There's a little caveat that maybe we can discuss offline, but essentially that. And then you build this other meta algorithm, if you wish, that says that if you use these other algorithms as parameters, and then you do this trick that you swap a bid and ask, then your algorithm has the guarantees. It inherits the guarantees of the other algorithms, that is. So given that the other algorithms, optimal algorithms for, say, first price auctions are t to the 2/3, you keep the t to the 2/3 also.
So the bid part that helps the algorithms, sorry, the swap part helps the algorithms? Because I was wondering, how do you deal with that? Because it intervenes on what they actually do.
Yeah, so you have to do your computation correctly, but you can show that if you do this, where whenever you have the wrong bids, you give the opposite recommendation, you still have the same, or you can reconstruct the same feedback that you would have observed with the different algorithms that you can feed back. I don't know if it's clear on this, but you can feed back the feedback that you got as a bid to the algorithm that actually were supposed to give you the ask, and vice versa. Okay, it's easier if you see it written down, but the important thing is that when you do this, you never increase the regret. So you can show that the feedback is correct, that's very important, and the second part is that you do not decrease the regret with respect to somebody that was just following the algorithm normally. Yeah. Yes, Claire.
Can we think of this problem as a partial monitoring problem?
Yes.
And then why does the categorization of the partial monitoring problem, typically that will give to the 2/3 for like the higher problems, like why does it not apply to this?
So
like it gives lower bounds, right?
No, it's okay. I heard. Okay, if people didn't hear it, can we see this as a partial monitoring problem? And if so, why can't we use the normal 3 categories of partial monitoring problems to see that it's just a hard problem? Because so the standard results where you have root t, t to the 2/3 and t is for finite action spaces. So in that case, you have these only three options. When you have infinite action spaces, you can have in principle any number of rates. Any rate is allowed. So it's not trivial. I mean, I'm sure that there must be some characterization possible of partial monitoring with infinite functions also, but it's not trivial just to use that, or at least we didn't think it was. We didn't say. Thank you. Claire.
Okay, well, it's been a long day, so thank you, Tom, and
Thank you, Emily. Yeah, thank you, everybody.